Okay, lesson 2, atomic spectra. So there are 3 types of atomic spectra that you have to know about. So we have emission spectra, which is right here. What I want you to notice about that is that it has a black background and it has colored lines in it. And then we have an absorption spectrum, which is basically the opposite. We have a rainbow background with black lines. And then finally, we have our continuous spectrum down here at the bottom. That one has no lines in it at all, so no gaps. So we can say that it's a full rainbow. So we're going to begin by having a closer look at emission or bright line spectra. So an emission spectrum and a bright line spectrum are the same thing. And an emission spectrum is the set of bright lines. So this thing, we have bright lines in there. That's called an emission spectrum. Those bright lines are produced when the light from a hot gas element is refracted in a prism or split by a diffraction grating. So the idea is that right here, we have a glass tube. It's filled with an element, and when we heat up that element, as long as it's a gas, it will begin to glow with light. And in this case, it's glowing with kind of a purplish blue color. What's happening there is that all these colors up here, so this red, these 2 blues, this green, this other red one, when you combine all of those colors of light together, you get this purplish blue color that's coming out of the glass tube. And so if you look at that purplish blue light coming out of the glass tube through a prism, the prism will separate out the colors. And so you'll see each color individually, meaning you'll see the emission spectrum. Okay, now remember, a prism isn't the only way to split colors apart so that you can see them individually. You can also do that with a diffraction grating. And just so you know, a spectroscope, which is this thing here that I'm circling, a spectroscope is just a diffraction grating inside of a tube. Okay, the idea with emission spectra is that emission spectra are made when atoms drop to lower energy levels and emit photons. So the idea is, okay, let's say you have an atom, and then here, this is your ground state. And above the ground state, you have your excited energy levels. Normally, the electrons like to be in the ground state. That's where they are naturally. But if you heat up the atom, so if I erase this now and I say that this is a heated atom, when you provide heat energy, that gives energy that can actually push the electrons from the ground state up to higher energy levels. So now that the atom's been heated, the electrons are in higher energy levels. They don't stay there, okay? As soon as they move up to a higher energy level, they go, oh, I don't like it up here. I want to move back down to the ground state, because naturally electrons want to go to the ground state because that's where they're most stable. So then this electron that I just drew is going to make a transition back to the ground state. And when that happens, we end up with a photon, and we see that photon as light. So every element has its own unique emission spectrum. So if you heat up hydrogen gas, you see one set of colorful lines. If you heat up helium gas, you see a different set of colorful lines. And so this is actually how scientists know what elements make up stars that are really far away from us. If you look at the light coming from a faraway star through a diffraction grating, you can check what colors you see, and then you can match the colors to the known emission spectrums, and you can figure out what elements are there. Just a reminder, make sure that you don't look at the sun through a diffraction grating though. That would burn your eyes. That would be really dangerous. Okay, so we're going to look at cool versus warm gases. So consider hydrogen gas when it is cool. This is kind of what I was drawing before. When hydrogen gas is cool, the electron in hydrogen is in the ground state. And since the electron is in the ground state, the atom won't release any photons, right? That electron cannot drop to a lower level. And photons are only released when things drop to a lower level. So this cool hydrogen gas is not going to release photons. So that's why if you take a cool gas, so that just means a gas that hasn't been heated, you're not going to see an emission spectra. Okay, but then when we heat up the gas, the electrons in the ground state get pushed up to higher energy levels. So here I'm showing two different possibilities. So maybe we have enough heat that the electrons get pushed up to the second excited state, or maybe there's enough heat that the electrons get pushed up to the first excited state. Which one of these two things happens, it just depends on probability. You're not expected to be able to predict it. You just have to know that if you're providing heat, some of the electrons will actually move up multiple levels, some of them will just move up one level, and that's fine. And then the electrons are going to fall back down to the ground state in one of several ways. So where we see the red arrow, that's an electron just falling from n equals 3 to n equals 2. Where we see the blue arrow, that's an electron that's falling from n equals 3 all the way down to n equals 1. And where we see the yellow, that's something falling from n equals 2 all the way down to n equals 1. So each of these transition releases a photon of a specific color, and then that's where the emission spectrum comes from. So this is what you need to have memorized. This is tested quite often. You need to know the procedure for making a bright line or an emission spectrum. So begin by exciting the gas by heating it. This pushes the electrons to higher energy levels. When the electrons fall back down to a lower level, the energy is re-emitted in the form of a photon, and so the gas glows with light. Remember, that's because electrons prefer to be in lower levels. The wavelength, and therefore the frequency and the color of the light produced, is determined by the difference in energy between the two levels. To see the individual photon colors, look through a diffraction grating or prism. And since elements all have their own unique energy levels, the color you see change depending on which element you use. Okay, next we're going to look at absorption or dark line spectrums. So reminder of what an absorption spectrum looks like there. So an absorption spectrum is the set of dark lines that correspond to frequencies of light that have been absorbed by a cool gas. So if you're doing a multiple choice question and it talks about absorbing and a cool gas, you know it's probably talking about an absorption spectrum. So an absorption spectrum is made when atoms move to higher energy levels and absorb photons. So here's an example of how you make an absorption spectrum. So you're going to start with white light. So here I have some kind of source of white light, like maybe just a white light bulb. And you're going to shine that white light through a cool gas. So what I want you to notice is the light that's just come off of this light bulb right here contains all of the colors of the rainbow, right? Because white light is just all of the colors mixed together. And all of those colors are going to be shining on this cool gas. And in this case, we're going to say that this particular cool gas absorbs the orange and the green photons. Now, which photons are absorbed depends on the type of gas, okay? So different types of gas are going to absorb different colors. Whatever this gas is going to absorb orange and green. So that means if we look at the colors coming out of the cool gas, it's not a full rainbow anymore, okay? You're going to have some colors of the rainbow, but then where orange was, you're going to have darkness. And where green was, you also have darkness because the color is missing. So that's exactly what you see here. If we just look back at the absorption spectrum, all of the colors of the rainbow are there, but there's darkness, and the darkness is because those colors were absorbed by the cool gas. Oh, I should just mention here too, in order to see the colors individually, you would still need to use a prism or a diffraction grating. So if you were just looking at right here where I've circled and where I'm putting the star with your bare eyes, you wouldn't see the colors individually, you'd just see a mush of colors. But if you looked at this through a prism or through a diffraction grating, then you would actually see the proper absorption spectrum. So this goes with what we were talking about yesterday. Remember how yesterday when we were doing some of our examples, we talked about how atoms can absorb photons, and it will absorb a photon if the photon has the perfect energy to bump the atom up to a higher energy level. That's what's going on. So here, any color that didn't get absorbed, so like red wasn't absorbed, red must have an amount of energy that's not allowed. Whereas like orange, because orange was absorbed, whatever the energy of that orange photon was, it must have been the right amount of energy to bump an atom in the cool gas up to a higher energy level. Okay, continuous spectrum. So as we said earlier, a continuous spectrum has no bright or dark spectral lines. It's just a full rainbow with no lines whatsoever in it. And you just have to know a continuous spectrum is produced by white light passing through a prism or diffraction grating. So there's no gases involved here. Okay, remember that for an absorption spectrum, it's white light moving through a cool gas. For an emission spectrum, it's a heated gas. Here, no gas at all. It's just white light going through a prism. And we already know that when you see white light through a prism or through diffraction grating, you get a rainbow. And you should also just memorize that hot, dense objects, so solids, give off white light. You might kind of know this intuitively if you take like a metal bar or something and you heat it up to a really, really high temperature like they do in welding. That metal bar will begin to glow, and when it gets hot enough, it will glow with white light. So there's just a summary of how each type of spectrum is produced. So continuous spectrums on the top, we have white light going through a prism and then landing in someone's eye. Emission spectrums in the middle, we have hot gas going through a prism, then landing in someone's eye. And absorption spectrum is at the bottom. We have white light going through a cold gas, then the light that has passed through the gas goes through a prism, then that's what we look at with our eye. Okay, don't forget that diffraction gratings and prisms change the order of the colors, and they also sort of behave a little bit differently. So diffraction gratings produce multiple spectra. So here, okay, in the middle of this diagram where this arrow is pointing to, we see our hot gas. And so at that location, we're seeing a whole bunch of colors mush together. So we're not seeing a rainbow, we're seeing something else. And that's where n is equal to 0. And then right here, okay, where we see this first set of colors, that's n equals 1. And then if I go out, so here and over here where I'm seeing the second set of colors, that's n equals 2. So when we look at this diagram, we're not just seeing one spectrum, we're seeing multiple spectra. There's 4 of them on this diagram. 1, 2, 3, 4. Oh, and remember with diffraction gratings that red diffracts best. So what that means is if you're looking at the rainbow here, the red color is furthest away from the central bright spot, whereas blue and violet are closer in to the central bright spot. Okay, and then remember prisms use refraction and the rule blue bends best, and prisms only ever make one spectrum. So here we have a gas discharge tube, it's filled with hot gas and it's glowing. We're sending the light from that through a prism, and over here we see our set of bright lines, but it's just one set of bright lines, right? It's not like there's 4 colors in it, but it's still just one set. And that's the end of the lesson.